Alright, so it's Saturday night and I'm about to post a video about inverse trig functions. I hope you enjoy.
First, just take a quick look at the graphs of trig functions as just as a little review, and then we're going to be looking at the inverse trig functions graphs, and we will be talking about the derivative of inverse trig functions. First, a look at the inverse sine function, also known as arcsine, or you might also see it written as sine -1. That also means the inverse of sine. This graph has a domain, if you can see from the graph, from -1 to +1, both of those included. And then it has a range from -π/2 to +π/2, and both of those are included as well. And then looking at the inverse cosine graph, or arc cosine, can you identify the domain and range? The domain here is also -1 to 1, and then the range of the inverse cosine graph is from 0 to pi. Okay, so we have the inverse tangent function, whose domain is all real numbers from -infinity to +infinity, and the range is from -π/2 to π/2. Now, the inverse cotangent function is a really interesting one. I have this graph here, which is what most math softwares would produce for the inverse cotangent graph, but it's not the one that your book uses, and it's not the one that we're going to be using to talk about the inverse cotangent function. And it might be interesting if you did your own research on which graph is more valid. Anyways, that's a conversation for a later date. So let's look at the graph of the inverse cotangent that we'll be talking about. We're going to be honing in on the cotangent graphs piece that is highlighted in this picture. So this is cotangent of x. We're going to be looking at this piece right here and talking about the inverse of that. So our range is going to be from 0 to pi, because remember we're talking about the inverse, so the domain and range switch. So we're going to be looking at this graph for arc cotangent or inverse cotangent down here. So this graph has a domain of all real numbers from -infinity to +infinity, and it has a range going from 0 to pi. Alright, so with the graph of the inverse secant, we have a couple of breaks here in the graph, this little discontinuity here, but we wouldn't necessarily call those asymptotes because these points are actually included. So the domain is going from -infinity until we get to that point at -1, and then it starts up again at +1 and continues to +infinity. Now the range of this function, as you can see by the graph, goes from 0, which is included, until we get to pi/2, which is an asymptote here. It's a horizontal asymptote. And then again continues from pi/2 to pi. And pi is included. And then looking at the graph of the inverse cosecant, so arc cosecant, we have a domain from -infinity to -1, and then from 1 to infinity, so same domain as the arc secant or inverse secant, and then our range here is going to be from negative pi over 2 to 0. So negative pi over 2 to 0. And then in this case, 0 is a horizontal asymptote. And then we continue from 0 to positive pi over 2. Alright, just another quick refresher on evaluating inverse trig functions. Let's say you have the arc sine of negative 1/2. Well, what would that output be? Well, it's just simply you asking yourself, sine of what value gives me negative 1/2? So the arc sine of negative 1/2 is negative pi over 6. Another quick example, arc cosine of 0 is what? You think about it. It would be pi over 2. And then finally, if you had something like the inverse sine or arc sine of 0.3, well, that's not something you can do in your head, so you could actually evaluate that using your calculator. And that would give us an approximate value of 0.305. So this type of evaluation would be done using your calculator. Let's review real quick how to solve an equation involving an inverse trig function. So, for example, let's say you were given the following equation. Arc tangent of 2x minus 3 equals pi over 4. So before we can solve this, we want to rewrite what the arc tangent means, and it means tangent of pi over 4 equals 2x minus 3. So we would write tangent of pi over 4 equals 2x minus 3. So now we can evaluate what the tangent of pi over 4 is, and that's just 1. So now you're just solving the equation 1 equals 2x minus 3. Solve this for x, and you get 2. Finally, what you've been waiting for, the derivatives of inverse trig functions. And you definitely want to memorize these. So the derivative of arc sine of u, we would say y prime, is equal to u prime over the square root of 1 minus u squared. So the derivative of arc sine of u, where u is some function of x, is u prime over the square root of 1 minus u squared. Alright, the derivative with respect to x of arc cosine, so I guess I should be using this notation. Make sure you understand this is the derivative with respect to x. The derivative with respect to x of arc cosine is negative u prime all over the square root of 1 minus u squared. So the only difference there is that this one is negative for the arc cosine. Okay, for arc tangent, the derivative with respect to x, I'm switching my notation, is equal to the derivative of u with respect to x, but I'll just write u prime, the derivative of u over 1 plus u squared. And you'll notice from the activity we were working on that this is what is going to help you do that problem number 7 on the u substitution activity. Alright, moving right along, the derivative of arc cosecant, or inverse of cosecant, the derivative with respect to x would equal negative u prime all over the absolute value of u multiplied by the square root of u squared minus 1. Alright, the derivative of arc secant is u prime, positive u prime, all over the absolute value of u multiplied by the square root of u squared minus 1. Finally, the derivative of arc cotangent, or the inverse of cotangent derivative, is negative u prime divided by 1 plus u squared. So this one is very similar to arctangent, it's just the negative u prime. Alright, so let's see a few examples. First example, find the derivative of arc sine of 2x. So I recommend pausing the video and working it out on your own. So the derivative of u, or 2x, is just 2, all over the square root of 1 minus u squared. So 1 minus 2x squared would be 4x squared. That's it. That's our derivative. Alright, second example. Let's do the derivative of arctangent of 3x. So just look at your rule, try this one on your own. So we would get u prime over 1 plus u squared, which would be 3x squared, the whole thing, which would make that 9x squared in the final answer. Alright, third example. Let's take the derivative of arc sine of radical x. Alright, so the derivative of the square root of x is 1/2 x to the negative 1/2 all over the square root of 1 minus, now in this case the square root of x squared just leaves me with x. And just to clean that up a little bit and simplify things, I could rewrite this as 1 over 2 times the square root of x minus x squared. Alright, last example. Let's find the derivative of arcsecant of e to the 2x. Try it on your own first, but I'm going to work it out. So, in order to take the derivative, first we want to take the derivative of u, which is e to the 2x. So the derivative of that is 2e to the 2x, divided by, now we're going to take the absolute value of u, so e to the 2x, times the square root of u squared minus 1. Well, e to the 2x squared is just e to the 4x minus 1. And now these will cancel, and you're just left with 2 over the square root of e to the 4x minus 1. Alright, we're going to stop there, and we will work on the integrals of inverse trig functions at a later time.